Hello AP Advanced Physics students. By now you should have watched the 2 MIT videos by Walter Lewin on electric forces and electric fields. Since we're missing school again today, I wanted to go through a couple calculations on how to calculate electric forces when there are multiple charges present. We're first going to start out with a simple charge configuration. We're going to start out with 3 charges here. Positive Q, here's another positive Q, and over here I'm going to put a negative Q. Now we're going to call this charge 1, we'll call that charge 2, and we're going to call that charge 3. All of these charges are equal in magnitude. Obviously, charge 3 is a negative charge, opposite in sign from charge 1 and 2. What we're going to do is we're going to say that Q1 and Q2 here are a distance d apart, and Q2 and Q3 here are also a distance d apart. And what I want to know is what is the net force on Q1 in terms of Q, d, and fundamental constants. A fundamental constant, for example, would be K, Coulomb's constant. First of all, if you remember back to the first video on forces, and if you reflect back to last year, the force, the electric force on a particle is equal to K, Coulomb's constant, which is 9 times 10 to the 9th, times Q1 times Q2, divided by the distance between them squared. So it looks very similar to Newton's universal law of gravitation. So if we first look at, so I want to know about the force here on Q1. So let's first draw some force vectors on Q1. And when we do this, when we look at net forces on a particle, we want to look at the force contributed by each of these separately. So first let's ignore Q3 out there and we'll look at the interaction between Q1 and Q2. Now both of these are positive charges, which means that the force between them is a repulsive force, which means that force apart from charge 2 is actually exerting a force here to the left, and we'll label that force of 2 on 1. The other force that's coming in this picture is from Q3 here. It is opposite in charge to Q1, which means that its force is an attractive force. Now, according to Coulomb's law, if the force is KQQ over R squared, and if these are all equal in magnitude, then the fact that this one is twice as far away as Q2 means that it must be exerting a weaker force than Q2 here. So I'm going to draw the magnitude of my arrow a little bit smaller. Here is the arrow, and we'll call that force of 3 on 1. Alright, so my net force, then if I just look at my diagram, I can see that the net force is the difference between those two forces. So F2 on 1 minus F3 on 1. Now, in my answers, I can only have Q, D, and fundamental constants. So what I need to start doing is plugging in what these forces are. Now, if electric force is KQQ over R squared, when I go here to solve and plug in for force of 2 on 1, of course, I have K, Coulomb's constant, times Q1 times Q2. And that's all over the distance between them squared, which is d squared. And from that, I'm going to subtract, so let's plug in our other force, 3 on 1, which is K, Q3, Q1. And this distance isn't d squared, right? It's 2d squared. So 2d squared, that whole quantity squared, not just the d. Now, I can't leave it like this because I'm only allowed Q, D and fundamental constants. And while K is a fundamental constant, that's good. D's are good. I can't have Q2 or Q1 in there. So I need to get rid of Q2 and Q1 and 3 and substitute in for Q. Now, if all Q's are equal, that's fine. Then I just have Q times Q, which is Q squared. All right, so let's further simplify this here. And we get K Q squared, since Q2 and Q1 are equal, all over D squared. And same thing over here. I have K Q squared all over, and now let's distribute this 2 here, so we get 4D squared. Now, if in the absence of time, I would leave it like this. However, always simplify your answers if you have time. Remember, when you deal with fractions, you can't just subtract these straight out. We need the denominators to be the same. So I'm going to multiply the top and the bottom of this fraction by 4. And now I can solve this because everything here is the same. And I end up with 4 over 4 minus 1 over 4, which is 3/4 K Q squared over 4D squared. And that is the net force of the particles, the charged particles on charge Q1. All right, let's do something a little more complicated. Let's throw in another particle. All right, so I'm going to turn this one on its side now, and I'm going to make these all positive charges. Positive Q1. Actually, let's take out the middle charge. We'll call that's Q2, and these are going to be equal, although I guess I didn't quite draw them the same size. We'll call that Q2. And let's go out some distance x away from this. We're going to put another particle, and that's going to be also a positive Q, and we'll call that Q3. And what I want to know is, what is the net force on Q3, the F3 net, in terms of Q? How about D, X, and fundamental constants? Again, that would be K. All right, so, oops, I forgot the D's. Here we go. Here to this position here, that's D, and that is also D. So again, let's draw some force vectors. If we're looking at the force on particle 3, it's coming from these two forces. Force from charge 1, right? Forces act in a straight line, and so if I draw a force vector, if I could draw a straight line, which that's not very straight, is it? Anyways, it should look something like this. So we'll call that F13, the force of charge 1 on charge 3. It's positive, they're both positive, so that's a repulsive force. And here we go down to charge 2, and we draw another force vector. It doesn't look quite the way I wanted it to look, but work with me here. There's force of 2 on 3. Whatever. All right, so if we look at our picture here, we see we have two forces that are both acting at an angle to our coordinate axes. In fact, let's draw coordinate axes here. So here is the positive x-axis, here's the positive y-axis. And remember that with vectors, anytime a vector is not on an x or y axis, we either need to rotate the axes or we need to split those into components. What I'm going to do is we're going to split these into components. So force 2, 3 has an x component. Right, there's force 2, 3x. And of course it has a y component, which is vertical, force 2, 3y. And force 1, 3 here also has a positive x component, force 1, 3x. And it has a vertical component, force 1, 3y. All right, so we're going to have a net force in the y direction, which will be F23y minus F13y, and we're going to have a net force in the x direction, which is going to be a sum of F23x plus F23x. Sorry, 13x. Now, let's think about Coulomb's law here, right? Coulomb's law says that the net force between two particles is K Q1, Q2 over R squared. In this case, our R value, right, is this distance right here. So this is the R for this particle, and of course there's the R for that particle. Now, hopefully I can convince you that this triangle made here by these two particles is equal to this triangle here, right? They both have sides D, they both have another side of length x, which means that this R should be equal to that R. Now, if these distances therefore are equal, and if these charges here, these two charges, are equal in magnitude, and I guess I should have written that, Q1 is equal to Q2, which is equal to Q3. If these are all equal, then what that should tell you is F23 must be equal to F13, right? Because the charges are the same and the distances are the same. So what that means for us, if we take a look, and let's use this angle theta right here. All right, that would be the same as that theta, and this theta would be the same as that theta. And while I did a lousy job drawing the triangles, again, if we look at the sides, D, X, R, if these triangles are the same, then these two angles are the same. And if these two angles are the same, then F23y must be equal in magnitude but opposite direction of F13y, which means that when we subtract these, that is going to give us 0, equal but opposite. And like I said, I did a lousy job drawing my triangle, so you can't really see that by looking at my picture. The x components, however, are both pointing in the same direction, which means they add together. So let's write our equations for our forces in the x direction. Now, in the x direction, force 2, 3 would be K. Q1 and Q2 are the same, so I'm just going to skip right away to calling that Q squared over R squared times the cosine of theta, right? This is the cosine of the angle. And of course, I'm looking for the net force, eventually the net force, so we're just going to go right to the cosine. And to that, I'm going to add my other force, K. Again, 1 and 3 are the same in magnitude, so I'm just going to write Q squared over R squared times the cosine of theta. Now, if these triangles are the same, then both of these quantities should be the same. So I can further simplify this by just writing this as, just adding these together and calling it 2k q squared over r squared times the cosine of theta. Now I'm not done, right? Because while k is a fundamental constant, good, q is an allowed variable, r and theta are not allowed variables, right? dx are allowed variables, they're not in there. So that means I need to rewrite both this r and that theta in terms of the variables d and x. All right, well, let's take a look at how to figure out what r is. Okay. R is the hypotenuse of this right triangle. All right, that's what r is. And if it's the hypotenuse, right, by Pythagorean theorem, r squared is equal to x squared plus d squared, right? Or r, right, is therefore the square root of x squared plus d squared. Now remember, these are the same triangles, so this r is in fact equal to the same thing. All right. So for r squared, then I can just plug in x squared plus d squared. All right. So let's do that. And I get, this is actually f net total, right? Because I put in the cosines to get rid of the x. So I have now 2k q squared over r squared, which we said was equal to the magnitude of x squared plus d squared. But now I have to get rid of the cosine of theta. All right, theta is not an allowed variable according to my problem description, but that's okay because I can write theta in terms of this triangle. All right, if I look at this triangle, I say that the cosine of theta is equal to x over the hypotenuse r, and of course r is not an allowed variable, so let's plug that in right away, which is equal to the square root of x squared plus d squared. All right, so now I can get rid of the cosine theta. I can replace it with this quantity, and I end up with 2k q squared over x squared plus d squared times the cosine of theta, which is equivalent to x over the square root of x squared plus d squared. Now, of course, we can actually simplify this. This denominator, right, would be the same thing as x squared plus d squared to the 3/2. So I'm going to rewrite this again in more simplified form. 2k q squared x over x squared plus d squared to the 3/2. And that is my final answer for the net force on particle 3. All right, let's throw another charge in here. Why not, right? So let's redraw this here. Here is our first Q. Here at distance D, now we're going to throw another positive, oops, what am I doing? We're going to throw another positive charge in here. Also plus Q, so that's distance D. And then again, another distance D, we're going to have another Q. 1, 2, 3. And at a distance X from that Q2, I'm going to throw in a positive Q. And again, this is distance D. All right, so now I've got 3 charges, and I want to know what is the net force here. We'll call that Q4. So I want to know F4 net. Again, we're going to do this in terms of Q, D, X, and fundamental constants. All right, so let's draw our force vectors here. Our force vector from the first one. Here's F14. For Q3, there is F34. And here is Q2. F24. Now, does it make sense to you that I drew the force on 2,4 to be a little bigger? Remember that Coulomb's law, right, is Q over R squared. Now, again, all our Q's are going to be the same, just like they were in the last problem. Remember here that R, right, our R value hasn't changed, our triangle hasn't changed, right? So R is still the square root of x squared plus d squared. right? Which makes it, if we're squaring x and adding something to it and then taking the square root, right, that means the hypotenuse is bigger. The hypotenuse is always bigger in a triangle, which means these forces are coming from charges that are farther away, right? D squared, or r squared, means that if this one is closer, it must be exerting a larger force. Now, again, let's throw up a coordinate system here. There's x, and there's y, and you can see that, again, these two forces are not on the x or y axes, so we need to break them into components. There's F1 for x. Kind of looks like a y, doesn't it? And here's F1 for y. And of course, this one up here has F3 for x and F3 for y. All right, so our F net, and I guess I should have said this last time, right? F net is going to be the sum of all of these forces. We have forces in the x and y direction, right? So F net is going to be the sum of our x and y components through Pythagorean theorem. So F naught would be the square root of the sum of the fx squared plus the sum of the fy squares. Of course, last time the y components were 0, so you know the square root of a square is just the same as fx. Let's see if that's the case again. Let's take a look at the net force in the y direction. Net force in the y direction. I have two forces here. I have F3 for y up and F1 for y, that's supposed to be for y down. And again, if these two are equal in charge and their r values, their distance values are the same, then they must be equal. They are opposite, which means just like in the last problem, our net force in the y is equal to 0. All right, well that's going to eliminate that part of my F net calculation, which means that my F net is the square root of the sums of the fx's. So my fx's, we have 3 now, right? We have F3 for x plus F1 for x plus this new one, and we have F2 for x. Now, if we think back to the last problem we did, right, the only difference between this problem and the last problem we did was this extra charge here, right, which means that my net forces 3 4x and my force F1 4x are still the same magnitude as they were in the last one, right? And we came up in the last one with our F net being 2 times kq squared x over x squared plus d squared to the 3 halves. Right? That was our answer to the last problem. Now, we can go through and derive this all over again. Right? We can say that F34 is kq times q, right? That's q squared over r squared, which would be x squared plus d squared, times the cosine of theta. Again, if this is theta, then that is theta, right? These are my thetas. And again, cosine of theta would be x over the hypotenuse, which is square root of d squared x squared, right? That's where the half part comes from. The 1/2 part comes from in the 3 halves here. So instead of going through all of that all over again, I'm just going to write that straight out. So that was our force from the last time, 2k q squared x over x squared plus d squared to the 3/2. But I have a new force here now that I need to add. That's F24, right? And F24 by Coulomb's law, Coulomb's constant, times Q2 times Q4. Again, these are all equal in magnitude, so I'm just going to write that as Q squared. All over the distance between them squared. The distance between them there is now not some fancy form of x, it's just x, right? The distance between here and here is just x. So I'm going to put that over x squared. Now it is completely horizontal. It is on the x-axis, so I don't need to take a cosine. I can just leave it the way it is. And I don't see any way to further simplify this. I mean, I guess we could take out k and the q squared. We could make a common denominator, I guess, but I'm just going to leave this like this and call it a day. Being able to apply the principle of superposition, that's what this is. The sum of the force on a particle, or the net force on a particle is the sum of all the forces on a particle, is something that I expect you to do. So I would like you now to go to your homework and start working on the force problems.